Hello, my name is Ningchuan Zhang. I'm a postdoc at the University of Pennsylvania working with modern learning. Thank you very much for watching my research description video for the ECHT networking event. This year, I'm on the job market for both tenure track and postdoc positions, so I really appreciate this opportunity. So today, I'm going to talk about a major theme in my research, the connections between algebraic K-theory and L-functions. Before I talk about my results, let me give you some backgrounds. I'll start with L-functions. L-functions are generalizations of the Riemann zeta function. Examples of them include the Dirichlet zeta functions of number fields, the Hecke L-functions of modular forms, the Artin or Dirichlet L-functions of color repetitions, and the V L-functions of algebraic varieties over finite fields. As you can see from the definition and examples, the study of L-functions touches many different areas of mathematics, including complex analysis, number theory, representation theory, and algebraic geometry. They are also featured in many major open questions and ongoing programs in mathematics, like the Riemann hypothesis, the long-length program, and the Birch-Schwimeter-Dyer conjecture. The other side of the connection is algebraic K-theory. Roughly speaking, algebraic K groups of a commutative ring capture essential information of linear algebra or homological algebras of R modules. The zeroth algebraic K group R is related to its Picard group. In good cases, the first algebraic K group R is the units in this commutative ring. Higher algebraic K groups are much more complicated to describe, but they are defined as homotopy groups of a space or spectrum K of R constructed out of the general linear group of R. And we can define algebraic K theory in more general setups, like we can define algebraic K theory of schemes. And there are many different constructions of the space K of R. Those constructions, they involve algebraic geometry, homotopy theory, and higher category theory, etc. Now let me tell you some known connections between the two sides. So L functions are complex analytic functions. So it is a natural question to ask what are the orders of vanishing of those functions at its 0 points. And turns out this corresponds to the dimension of rational algebraic K groups. At certain points, L functions may take value in algebraic numbers, and those special values correspond to the size of torsion subgroups of algebraic K groups. We'll see in an example how those two connections work explicitly. And L functions also have a symmetry called functional equation, and this corresponds to the certain duality phenomenon on algebraic K series spectrum. And well, I don't know what the actual Riemann hypothesis corresponds to in algebraic K theory, but the Riemann hypothesis for the VL functions of algebraic varieties over finite fields, they correspond to power operations on algebraic K series spectrum. And here's a concrete example. Let F be a number field, OF be its ring of integers, and zeta F be its Dirichlet zeta function. Then we have Quinn and Borel show that the order of vanishing of zeta F at negative integers is equal to the dimension of rational algebraic K groups in all degrees. Then in the celebrated Quinn-Ningchuan conjecture proved by Rowalski-Rost, this shows that the leading coefficient in the Taylor series of the Dirichlet zeta function at negative integers is equal to plus minus the ratio between algebraic K groups of OF times a transcendental number called the Borel regulator. And those two theorems, the left-hand sides are defined analytical properties of zeta function, which are defined purely analytically. The right-hand side are either dimensions of a vector space or size of a finite dimensional finite abelian group. So the right-hand sides are defined purely algebraically. So those two theorems illustrate very deep connections between L functions and the algebraic K theory. So in my own work, a general goal is to generalize the connections between algebraic K theory and L functions above to Dirichlet L functions, Dirichlet or Artin L-functions by twisting algebraic K theory with color repetitions. In my thesis, I constructed analogs of Dirichlet L-functions in chromatic homotopy theory, such that their homotopy groups capture the denominators of special value of L function. and satisfy a duality phenomenon resembling the functional equations of the L function. In my recent preprint, I generalized the Quine-Borel theorem to Artin L-functions by applying rational equivalent homotopy theorem to an algebraic result of growth. And finally, in my ongoing project with Artin Elemental, we try to generalize the Quine-Ningchuan conjecture to Dirichlet L-functions, and we have made some progress. Certain cases have been verified by computing equivalent homotopy groups of algebraic K-series spectra of number fields with coefficients in those characters. And that's it. Thanks for your time and attention.